So first of all, I want to thank the organizers for inviting me here to give a talk. It's been a great workshop so far, I think, and it's an honor for me to speak here. Even though I have to admit it was really Abdul Latif, who is listed as the co-author here, who should have given this talk. He had to decline because he's getting married tomorrow morning in Oxford. And I think his wife would not have been happy with this. Anyway, so this is how you ended up with me here. I hope you bear with me. We're going to end this day the way that we started it, with these squares approximations, with the additional twist that I'm going to talk about a multi-level version of this, which allows you to save computational cost in many practical applications where the function that you want to approximate actually comes, you cannot evaluate it exactly, but it comes with a tuning parameter that allows you to trade off accuracy versus cost, as Jan mentioned in his talk this morning. Okay, so since we've already seen the talk of Albert about the least squares approximations, I made this part a bit shorter than originally planned, and I added a section on the connection between multi-level algorithms in general and a general version of Smolyak's algorithm. So in particular, this is going to allow you to see multi-level algorithms as just a particular case of Smolyak's algorithm, if you write it down in sufficient generality. Now, the motivation where I'm coming from is as in Albert's talk and in other talks before mine, that I'm looking at parametric PDE or random PDE as a recurrent uncertainty quantification. So we don't want to only solve the PDE once, but we want to solve it for all possible values of some parameter y. More specifically, in this talk, I'm going to focus on just tracking scalar valued response surfaces. So I'm going to track the dependence of a quantity of interest f of the solution on this uncertain parameter y. The reason you might want to do this is you might want to compute statistics, covariances between different input parameters. You might want to build the probability density of the quantity of interest, which becomes easy once you have the response surface. You might want to give performance guarantees, consider worst case scenarios, or we've also already seen inverse problems where you want to infer the true value of the parameter y. So you assume there is a true value based on some observations of the solution. And in this case, you need to solve this forward problem, for which I'm going to build here surrogate functions a lot of times. So it's important that you have a fast way to approximate this and to evaluate this surrogate response surface f. Okay, so now to recapitulate what we've seen this morning, I have one slide. And I applied some random permutation of the notation, so you got to be careful and keep an active mind. So we're going to just assume that we have a general function f in some Lebesgue space on a domain gamma that is equipped with a probability measure mu. And we assume that we want to approximate this function f by a multivariate polynomial, and that we are only allowed to use to find this polynomial using point evaluations of this function f. The way this works is that you first fix a finite dimensional subspace V. And of course, in practice, you have to choose this space based on some a priori information of your function f, such that the space is even able to capture important properties of this function f. But that's not what this talk is going to focus on. Just as Albert, I'm just going to assume that I have, later on, I'm going to assume I have a sequence of polynomial subspaces in which you get certain approximation rates. And then to find a function in this polynomial subspace, what you do in least squares approximations and random least squares approximations is that you generate random samples, this time from a sampling distribution nu, which does not have to be equal to the underlying probability measure mu. And then finally, you define your least squares approximation as the polynomial in your subspace that minimizes this discrete L2 norm here, which has the Radon-Nikodym derivative of the underlying probability measure in which you want to find your approximations or measure your approximations with respect to the sampling measure that you used to make up for this kind of important sampling that Albert has talked about. Okay, now since this is an unbiased, or the square actually, it's missing the square of this discrete norm is an unbiased estimate of the continuous L2 norm, so you would guess or you would hope that using this method you get roughly the accuracy that the continuous L2 projection would give you. And now I have one more slide that summarizes these results about the accuracy. The first one is simply and you can prove this using simple linear algebra, that to even have a unique minimizer of this least squares problem, you need at least as many samples as the dimension of a polynomial subspace. Then the next result was that if you use the underlying probability measure to generate your samples, then usually you get a power of your dimension of the polynomial subspace to ensure that you get such quasi-optimal polynomial fits. And this power is usually larger than 1. So for example, if you look at the high-dimensional Lebesgue measure, it's equal to 2. If you look at Chebyshev measure, it's somewhere between 1 and 2, and so on. And now the main result of this morning's talk was that it uses a specific choice of the sampling measure. And this choice depends on the polynomial subspace in which you want to find an approximation, and it depends on the underlying probability measure. Then you get roughly the same result. And on the next slide, I'm going to be more specific and list these results. But this time, you only need m times log m samples. And so the exponent is always equal to 1, no matter what your underlying probability measure is. Yeah, I'm going to put this in the next slide. I'm sorry. I just wanted to first give a general overview. And now this is the specific result, which I state under the assumption that the polynomial space is downward closed. It's a sufficient but not necessary assumption, and it just means that if you have one monomial that is in your subspace and you have another monomial whose degree is smaller in each component, then this one is also in your subspace. And in this case, you get this first result here that if you use the underlying probability measure to generate your samples, then you get this m times log m behavior, m to the power b times log m. And quasi-optimal means that your polynomial approximation is as close to your function that you're interested in as possible in your polynomial subspace, up to a constant c, which it's important that this constant c is independent of the number of parameters and is independent of the subspace. And now, of course, since this is a random method, it can, of course, always break down if you have bad luck. But this chance that you actually have bad luck decays super algebraically. So it decays at arbitrary algebraic rates, r, which will then just affect this constant of the number of samples. And as far as I know, this dependence is actually linear. You can also get, and we've seen it this morning, you can also get results that are similar like this that have an L2 norm here. If you exploit, for example, that you have an explicit knowledge of a supremum bound of your true function f, if you exploit this, you get also the L2 norm on the right-hand side. And then it's really a quasi-optimality result. Now, we've seen the second case, the weighted case, which stated that if you use this optimal sampling distribution whose density with respect to the true distribution is given by this average of squared orthonormal basis functions, then you get rid of this b in the power of this m. And you get basically the same result. In this case where you have this L infinity probability result, you get an additional weighting here by the inverse of this density, but you can also formulate different results where this does not show up. Now, if you see these results, you might have two questions. The first one, how do you actually generate samples from this optimal distribution? And we've already seen this morning one way to do this using these conditional distributions. I'm going to present another one in a bit, so you can decide for yourselves which one you prefer. And the second one is whether there is some analysis of these optimal distributions, if we can do some a priori analysis on how they behave. Okay, now first of all, the algorithm that I think that I personally found easiest to sample from this optimal density is that you just interpret it as a mixture of densities. Because of course, each of these basis functions, they are all non-negative. They all integrate up to 1. So you can simply randomly pick one of them and then sample from the corresponding measure. And in the case where your domain is a product domain, where you have a tensor measure, and where you use as an orthonormal basis tensor basis functions, you can do the second step. You can do all of the components independently of each other. And then for the to actually do these single components, you can use rejection sampling, and you can exploit some knowledge of how polynomials behave in 1D to make this rejection sampling efficient. And with this, then the final cost of doing the sampling is linear in both the number of parameters d and linear in the number of samples that you want to generate. The second question was about whether there's some analysis that can be done on these optimal distributions. This one I can answer partly in the case of a hypercube, where it can be shown that for many measures, and writing down the specific conditions would be a bit too technical. But for example, these families include Jacobi measures, so in particular they include Chebyshev measures and Lebesgue measures. This optimal sampling distribution is dominated, or dominates the uniform distribution, so and it is dominated by the Chebyshev distribution, which has this density with respect to the Lebesgue measure. And both of these bounds, these upper and lower bounds, hold to up to factors that are independent of this polynomial subspace V. So, for example, the lower bound can be useful to simply get rid of this weighting factor here on the right-hand side that appeared in the theorem before, and you just get a constant out here. That does depend on the number of parameters, though. The upper bound, if you see the upper bound, you might think that you can just use the Chebyshev distribution to generate your samples instead of the optimal distribution, because it dominates this the optimal distribution, and then it's pretty easy to show that actually you can do that, and then the number of samples that you need to achieve the same accuracy only increases by a factor that is independent of the subspace V, so it's simply this domination factor here. But this factor does depend on the number of parameters, and this dependence on the number of parameters is actually exponentially. So this is really not a good idea in high dimensions. An advantage, though, of using this Chebyshev distribution is that it's super easy to sample from. You just need to generate uniform random variables, and then you transform them with a sign. And as we've also seen in our Berg's talk this morning, adaptive algorithms are an interesting thing if you use these optimal distributions, because the optimal distributions, of course, change when you change the subspace. So then if you were being strict, you would have to throw away all of these samples each time you change the subspace. This, of course, wouldn't be the case in this case of this Chebyshev distribution, because it doesn't depend on the subspace V. Okay, now to lead to the main part of this talk, the multi-level part, let's recall that the function that we want to approximate in the motivation example, it actually required the solution of a PDE. And this is, of course, rarely exactly possible. And instead, what is possible is only that we can evaluate approximations of this function indexed by some h that could, for example, determine the finite element diameter in your PDE solver. And as this h goes to 0, your approximations converge to the true function, but they also become more and more expensive. Now, what I call the single level approach here, but which is just the straightforward thing to do, is that you just ignore this and you just fix one of those h's, and then you apply a least squares approximation to that h, to that function fh. The problem with this is, of course, if you want to have better and better approximations, you need larger and larger polynomial subspaces to capture this function f, and you need smaller and smaller h, which will mean more expensive samples. So, for example, I'm going to do some analysis just so I can compare it later on to the multi-level analysis. If you can establish that your finite elements converge at the rate h to the power beta, and then also that when you integrate this over the parameter domain, you get the same rate. And if the cost of these finite element solves grows like h to the power minus gamma, the gamma, for example, would depend on the dimension of the domain of the PDE. And if you also now can somehow establish that you have a sequence of polynomial subspaces in which you can approximate all of these response surfaces at a rate that is a negative power of the dimension of these subspaces, then, of course, to achieve a total accuracy epsilon. Do you have a question? No, okay. You get the total cost epsilon to the power minus, and then you get the sum of those two factors, the gamma over beta corresponding to the PDE solution, and the mon over alpha corresponding to the complexity of the polynomial approximations. Okay, and now multi-level algorithms that allow you to get rid of this sum in the exponent and just replace it by the maximum. And they do this by combining samples from coarse approximations of your response surfaces, meaning cheap PDE solves, with only a few more expensive PDE solves. And do this in, yeah. And okay, these multi-level algorithms, they are based on the fundamental idea to use a decomposition of your function f. And this is it's a telescopic decomposition. We just first write f as fh0, so a coarse approximation, and then an infinite sequence of corrections to this original coarse approximation. Now, if you want to turn this decomposition here, telescopic sum into a practical algorithm, we need to, of course, to truncate it and then apply least squares approximation to each term, or any other algorithm to each of these terms. And if we used the same least squares approximation, meaning the same polynomial subspace for each of these terms, then we would just do more work than in the single level setting, and we wouldn't gain anything. But the main idea now is that you have to think of this function fh0 as basically of the same order as the function f. So it might be shifted a bit higher here, a bit lower there, but it's approximately the same order, and it is cheap to evaluate. So it makes sense to first generate a lot of samples from this KAUST approximation to get a rough idea of all the coefficients of your function f. And the additional terms, the correction terms, though, they become smaller and smaller with larger L's, or with smaller h's. And they are also expensive. So for those, you actually don't want to compute a lot of samples. And instead, you only compute a few samples, meaning you use a small polynomial subspace that only gives you corrections in the most important coefficients of your function f. Okay, and based on this intuitive understanding now, you define a multi-level approximation by choosing an exponentially decreasing sequence of h's and exponentially increasing sequence of polynomial spaces. And then you define the multi-level formula by applying the least squares approximation with a large polynomial subspace that is applied to this cheap function f0. And then you add the correction terms where you use smaller and smaller polynomial subspaces to these higher order corrections that become more and more expensive. Okay, I already said that the result that we get is that only one of those terms in the exponent of epsilon remains. So if the cost of the PDE complexity dominates, then only this term gamma over beta will remain in the exponent. If the polynomial approximation properties of your function f are the ones that are the dominating one, then this term will remain. And as always, there's a trade-off which takes the form that you need slightly stronger assumptions to get a slightly stronger result. So in particular, you need to show that your function fh does not only converge to the true function f in a Lebesgue space or in some pointwise space, but in a norm on the parameter domain that entails polynomial approximability. So for example, in a CK norm or in a Hardy space norm. Okay, and this is now the more exact result. Namely, if you assume that your functions fh converge to the true function f in a space f on the parameter domain, and the space f has the property that functions in it can be approximated by polynomials at a rate, again, minus alpha times the norm of this function space, then you get the results that I mentioned before, and you get some additional logarithmic terms here who are known but are kind of ugly to write down. And you get the same kind of results that you get in the single level setting. You can write down the results in probability, that you get the accuracy with a high probability, where the failure probability decays super algebraically. And you can also get L2 bounds expected mean square convergence with the same rates, basically. Okay, now this is the only part of this talk where I'm actually going to do a bit of math, because I think the proof is quite instructive. It's super easy. It's basically just a triangle inequality and then a geometric series. So for the proof here, I'm going to assume that all of these parameters are just equal to 1. And so what we want to show at the end is then that the complexity is epsilon to the power minus 1. And well, to prove this, for any L, you can just write the difference between the multi-level approximation and the true function fhl by grouping all of the terms in this multi-level decomposition. So first group the term corresponding to f0, where you once apply the least squares approximation with v capital L, and once you have the identity on the other side. And then you do this for all of these correction terms. You apply the triangle inequality, and what you end up with is basically a sum where this term, it becomes larger and larger as L goes to capital L, and this term becomes smaller and smaller as L increases. And more specifically now, if you simply choose these sequences such that the dimension of this polynomial subspace increases exponentially and this h decreases exponentially, then this fact that this one grows, this one converges to 0, they cancel each other out, and what you end up with is just the exponential of minus capital L, which you get here once, and then you get the same exponential of minus capital L a number of L times in this correction from these correction terms. So basically, you just get mainly exponential of minus capital L. If you want about the work, it's even easier. The work is, of course, just given by the product of the number of samples that you need times the cost per sample. And then you sum this up over all of these different terms in the multi-level decomposition. And again, now what you get is that the number of samples that you need, since if you use optimal sampling, it's just linearly, log linearly in the subspace dimension. So you get, again, that you get something that grows. Now in this case, it's actually something that decreases, something that increases. They cancel each other out, and you end up with exponential of L. Now you just need to write this work bound in terms of this exponential of minus L that we had for the accuracy, and then you're done. And then to actually get the main the full result, you also need to do some bookkeeping of the probabilities that these operator norms, which I just stated that they behave like this, but they don't always behave like this, of course, because they only behave like this in probability. So you need to do some bookkeeping with this, but that's mainly the proof. Okay, now to show you that this also works in practice, I have one really short numerical example. So I'm going to solve this PDE that I had in the beginning, where we have just a Poisson equation whose coefficient is assumed to be a random field. So, and we parameterize it by using infinitely many random parameters uniformly between -1 and 1. And our goal is now, we assume that we want to do the simplest thing possible. Namely, we want to approximate the spatial average, meaning the average over the PDE domain, which is conveniently only 0 to 1. It's one-dimensional PDE. And the main point now is that if you look at the convergence result, you see that only the complexity of the PDE solve of the PDE part of this problem remains. So the convergence here is approximately epsilon to the -2, and this -2. I mean, the convergence is runtime to the power -2, and this -2 simply comes from the fact that I used piecewise linear finite elements. Okay. I think I'm going a bit fast. Maybe we can just have dinner earlier. Okay. Now, as I said, I'm going to also present to you the connection between multi-level algorithms in general and a general version of Smolyak's algorithm. And I hope that this maybe gives you a new perspective on multi-level algorithms and Smolyak's algorithm too, and maybe inspires you for some novel applications of this. So to introduce Smolyak's algorithm in generality, I'm just going to switch now and assume we have an arbitrary approximation algorithm that takes n discretization parameters k1 to kn and maps them to some output space. So for example, in the case of this polynomial approximation, you have two discretization parameters. You have the accuracy of all of your samples, and you have the size of the polynomial subspace that you want to use to approximate your function. But these discretization parameters, they could also be the number of quadrature nodes in high-dimensional integrals. It could be the number of time steps if you have time-dependent PDE. It could be the number of particles if you do particle simulations, or it could be a truncation parameter if you look at PDEs with infinite unbounded domains. So the examples more specifically, you can interpret polynomial approximation in this setting by just being an approximation algorithm that has two discretization parameters and takes values in the Lebesgue space. You can interpret the original setting that Smolyak was interested in 50 years ago as an algorithm that takes n different discretization parameters and then turns them into a multivariate quadrature rule by tensorizing univariate quadrature rules, where each of the discretization parameters controls the density of nodes in the different directions. Now, in this general setting, you have what I call cursive dimensionality. People in IBC don't, I learned today, which takes the form that often you can establish that the algorithm converges at a rate that is bounded by inverses, by a sum of inverses of these discretization parameters. And in such settings, you can, of course, simply achieve an accuracy epsilon by choosing all of the discretization parameters large enough. Now the cursive dimensionality now shows up since often the total work that your algorithm requires is the product of these of algebraic powers of these discretization parameters. So for example, in this polynomial approximation, your work is the number of samples that you generate, which is an algebraic power of the subspace dimension, times the cost per sample. In tensor quadrature, the total work is, of course, also just the product of the number of discretization nodes in the different directions. And in this case, then the total work is epsilon to the power minus, and then you again have this sum in this exponent. And now if you remember from the first part, there we were able to reduce the sum, which was only a sum of two terms, to the maximum of those two terms. So our goal now, and this is up to logarithmic factors, but our goal now is to prove the same kind of result, but for algorithms that have n discretization parameters instead of only two. And again, we're going to use some decomposition, and then we're going to truncate this decomposition efficiently. And to introduce now this decomposition, I think it's easiest to start out with a function that is defined on tuples of real numbers instead of tuples of integers. Because for such functions, it's easy and everybody can immediately imagine that you can write evaluations of your function f as integrals over mixed derivatives of this function, just by Fubini in the fundamental theorem of calculus. And now we want to have such a decomposition for our numerical approximation algorithm, which takes tuples of integers. So what we need to do is we define discrete derivatives, meaning differences, and we expand them by 0 to negative values. And then we define that decomposition, so that's just an iterated derivative. And then we can, this time simply using simple school algebra, write again the output of our algorithm as an iterated sum over these mixed differences. And in particular, if we already know that the limit exists, at least on a formal level, we can write this limit as an infinite sum of those mixed differences. Now to truncate this, as I said, you have to do it efficiently, and we already see that if you truncate this infinite sum in a rectangular fashion, then you just get back an entry, an output of our algorithm. So we wouldn't have needed to introduce this decomposition. But it's of course better to only retain those indices in this infinite decomposition for which the contribution of those corresponding mixed difference terms is large and for which the cost of those is small. So in particular now, if you assume that the work of computing these mixed derivatives behaves as a product of exponentials of the discretization parameters, and in particular you can, of course, if you have algebraic work, then you can just reparameterize to get this exponential behavior. And if you also assume that these mixed differences decay as a product of exponentials, and I'm going to show you later on how to actually prove that such a thing holds, then optimal index sets are given by these simplices and can then be shown, and it was shown by Smolyak 50 years ago for the case of tensor quadrature, and we wrote it down for a review article last year, but I'm sure that he wouldn't have been surprised by this, that the total work then required for accuracy epsilon is exactly what I said, that you just need epsilon to the power minus maximum of all of those ratios between work parameters and convergence parameters. And then you get logarithmic terms whose power depends on the number of these inputs for which this ratio is actually maximal. So it's given here. Okay, now to make the connection between this analysis, which has kind of a similar result as what you've seen in the multi-level analysis, and these multi-level algorithms are more specific, you need the combination rule, which states that for arbitrary index sets, so not only for simplices, but no matter how you truncate this infinite sum, you can always write the sum over the mixed differences as a linear combination of the outputs of your algorithm. For simplices now, if your index sets are simplices, there's even an analytic formula for this, which is due to Wasilkowski and Wozniakowski. And now, most importantly for our case, in the setting where you have two discretization parameters, the combination rule just turns into this multi-level formula. Because in this case, all of those entries here are just 1, -1, or 0. And what you end up with is that Smolyak's algorithm in this general setup reduced to the multi-level formula, which says that you start out with an approximation that takes a fine discretization in the first entry, really a coarse discretization in the second, and then it starts adding these correction terms. I told you that I was going to show you how to actually establish that such bounds on the mixed differences hold. And in this way, you will then get an alternative proof of the result that I've shown you before. And, well, one way to show that this holds is to exploit multilinearity. Multilinearity meaning that you can write the output of your algorithm as a multilinear map applied to sub-algorithms, each of which depends only on one parameter. And if you can then show that these sub-algorithms converge exponentially, then it's trivial to show that also the same holds for these mixed differences of the main algorithm, which simply holds because the mixed difference, I'm sorry if you can't read this, the mixed difference applied to the multilinear map just turns into differences within each of the inputs of the multilinear map, and you just use continuity and you get the result. So the way that polynomial approximation, of course, fits into this because the least squares approximation operator is a linear operator, and you apply it to a function. And it has nothing to do with this function being linear. It's just that this application of linear operators is bilinear. Quadrature also fits into this framework. So the original setting that Smolyak was interested in, that yields sparse grids, because applying the tensor product of operators is, of course, a multilinear operation. And in both cases, I think it's nice to see how the continuity of this multilinear map immediately shows you which domains you have to, or which norms you have to choose on the domains of this algorithm. Because of course the tensor product of operators is only continuous if you interpret it as a map on the tensor product space of the functions equipped with the tensor norm. There's also another general way to establish this decay of these mixed differences. Which, for example, you can use in the case of PDEs when you want to apply this to PDE solvers, and which states that if you can write the output of your algorithm as the limit plus some perturbations, each of which only depends on a subset of your discretization parameters, and if you now can show that all of these perturbations decay at the desired product form of exponentials, then the same thing also holds for your original mixed differences. Okay, now if you can't analyze your problem analytically, then you can always resort to adaptive algorithms. And there you can just, of course, in this general setup, you can do the same thing as people have always been doing for sparse grids. And but in particular, since we know and can interpret this multi-level algorithm as just a Smolyak algorithm, this way of using these sparse grid algorithms then leads to an adaptive algorithm for the multi-level case too. And this is done using just estimates of work and contribution of all of these mixed differences. And then you just maximize among all candidates that you have the ratio between those two quantities. And in doing this, you enforce downward closeness of your multi-index set to reduce computational complexity, and also because it's intuitive that if you have a downward neighbor that is not yet in your multi-index set, then it would sense to first add that one instead of the other index. So for example, this one wouldn't be a candidate in your search for a new index to add because its lower neighbors are not in yet. So you could first try to add all of this before you add this one. So how this works is that you just, for each of your candidates, you look at its lower neighbors that are already in your set, for which you know the contribution and the work. And then if you decide that this is, for example, the one that maximizes this ratio, then you add it and you add the corresponding candidates, and then you start again. Now to wrap it up one more time, the way that this general setup now corresponds to an adaptive algorithm in the polynomial approximation setting is that these three indices in the multi-index set, they would correspond to mixed differences applied to F0. And then this one would correspond to approximating using the smallest subspace, this corresponding to the difference of the first subspace and the zeroth subspace, and so on. So that those three indices together, if you sum in this direction, they correspond to what you've seen before, that you use a large polynomial subspace, V2, to apply F0. And then the next two indices, they correspond that you use a smaller polynomial subspace applied to the first correction. And this finally means that you add one more correction using only a really small polynomial subspace. Okay, and is that a question? Okay. Now, all of this, having it in this general setup allows you to write efficient adaptive algorithms for these kind of multi-index computations without having to redo it every time, depending on whether you do sparse grids or whether you do a multi-level or whatever you want to do. And in particular, Abdul Latif, who I'm stepping in for, did all of this, and he has this public as MIMClib multi-index Monte Carlo library, so you can also use it for multi-level Monte Carlo simulations. And I can really recommend it. It's open source. It has a Python interface, so it's easy to use, but it's really fast because Abdul is really good at coding. And yeah, it also allows you to do reproducible science. It archives everything you do in the SQL and so on. Okay, with this, I'm already at my summary. And so let's recap. What did you see? We saw that polynomial least squares approximation allows you to obtain quasi-optimal fits to functions up to constants that are dimension independent. And dimension means here the number of parameters. We have seen that importance sampling, meaning optimal distributions to generate these samples, allows you to reduce the number of required samples. And we've seen that it's quite easy to actually generate those samples from these, at first, a little bit complicated looking distributions. We have then seen that in the case where you cannot evaluate the function exactly, the most efficient thing to do is to first get a rough idea of all of your coefficients of your function by using a lot of evaluations of some cheap PDE solver. And then you only adjust the most important coefficients with less and less samples from the more expensive PDE solvers. And to actually analyze all of this, you do need some stronger assumptions. I didn't write this down, so in some practical applications of this, actually, you don't get exactly the maximum of those two rates, but you get something in between. But at least I can show that it never gets worse, no matter what your actual assumptions are at the end. And finally, we have seen that multi-level algorithms are nothing else but a Smolyak's algorithm written down in a general form. And to me, this is really helpful when I try to think of new applications of this, or when I try to actually write efficient numerical applications of this. Okay, and with this, I want to thank you for your attention, and I'm happy to answer a lot of questions.